Okay. Thanks, Chairman. And thanks to organizers for this wonderful meeting. In online meeting itself is really nice. Thanks to Ravindra and Satyavrata for this meeting. So this is the title of my talk, and some material is here in a Google website. Okay. So first, happy birthday, Sanjay. It was very nice knowing you. We have been discussing more with more vigor with recent times. And this is Sanjay's book, from which I learned a little bit about coarsening. So our field's kind of not in the same domain, but this coarsening problem we come across. I mean, I go to meetings and I see some talks on that, and I was wondering from this random states, how do we get this ordered state? Of course, it's known from dynamics, so many simulations, and so on. But if you look at from turbulence language, we see this kind of ordering in 2D turbulence. People who are aware of 2D turbulence would know that there is a structure formation, like vortex or hurricane is supposed to be 2D phenomena. Okay. Now, I was just wondered whether it is basically some kind of inverse cascade or not. Okay. So this energy flows from small scale to large scale. And I asked these questions to many people and experts. I really didn't get a clear-cut answer. So I thought I will work on this. Fortunately, Sanjay came for a colloquium last year in January, and we started discussing this. So he gave a 1 hour beautiful presentation privately in my office, and then we understood what the problem was, and then we started discussing. And I think we got somewhere from the energy flux perspective. There is no inverse cascade. There is a forward cascade, in fact, and I will just try to elaborate that part. Along with that, I will also talk a little bit about other things connected to StatMech, which I am trying to get into. I need some feedback from experts on those topics. So these are the things which are overlapping StatMech and fluid turbulence. So energy transfer, this is a book I wrote. This is a recent article which is about to come, where I discussed about energy flux. I think this is the most comprehensive thing on energy flux. And arrow of time, I'll talk about it. It wasn't in my agenda, but now I included it. And these are popular talks for students on multi-scale description. For example, diffusion. Diffusion in fluid turbulence for two particles which are close by, it goes as T to the power 3/2. It's super diffusive. Now, it's very easy to derive, and hardly anybody talks about it, why it is 3/2. Of course, in turbulence community, we know it very well, but I describe it in this article. So some people may like it. It's very lucid set of articles. In Research Matters, you have to type Research Matters or look at my website. I'm advertising few things. So there were quite a few talks on hydrodynamics, starting from Abhishek. Then JKB, Professor Bhattacharya gave a very nice presentation today morning. So that makes my job very easy. But for some people who are not there in the talk, let me just give a brief introduction, because the flux is, well, I mean, I came across flux in this field. Okay, I mean, this is my main area of research. So we start from Navier-Stokes equation. Okay, so this is an equation for fluid flows, and it is forced. Normally, Kolmogorov assumed that it's forced, and the viscosity is small. Okay, the viscosity is small and it's incompressible. We'll focus on incompressible, though Abhishek's talk had a compressibility, but basic features there will be some commonality, but there are of course uncommon features. So the idea is that we have a fluid in a, let's say, some container, and let's say water, and I stir this fluid. So we force at large scale. So that is what is the large scale forcing. And then we supply energy at large scale, and that energy cascades down to small scales. Okay. And that cascade, basically, we know that it gets heated. I mean, this is textbook material in schools. So there's energy flow from large scales to small scales, L. And there's a cascade, I mean, there's energy is flowing, like JKB told very beautifully, that for hydrodynamic turbulence and Kolmogorov picture, we supply energy at large scale. There's no energy in the no energy supply in the intermediate scales. We just force this stirrer or spoon is acting at large scale, no forcing in the intermediate scale, and there's a cascade. Okay, there's a reason why it's constant, which we don't want to get into, but there is an energy flow across scales. Okay, and this is one of the non-equilibrium features, and so pi in the inertial range let's call it wave number k, which is inverse of length. So we'll have k coming in between quite often. This is very common in fluid turbulence. You just do the Fourier transform, wave numbers will come. But it's a multi-scale problem. There are just lots of scale. In fact, it could be billions of modes. Okay, that is a really multi-scale problem, and it's often, of course, found in StatMech all the time. Critical phenomena is one such example, but this is constant in hydrodynamic turbulence. Okay, it won't be the same in coarsening, but I will come to that bit later. And we can also derive what is the energy content at different scales. Okay, so that is k minus 5/3 for hydrodynamic turbulence. Okay, that's known. Now, so this is a picture which I kind of like, that connects particles at small scale with large scale forcing. Okay, this describes multi-scale. I thought about quite a bit. Is there in that EPGA paper, European Physics Journal paper. So we supply energy at large scale, and this some kind of representation of the large eddy. We have a large eddy sitting here that breaks into smaller eddies. You can see this if you have a glass of tea and pour milk on it. Okay, then you see a lot of filaments. In fact, it's very nice to see. It's very easy. You can see it yourself. We pour milk, it just fragments into small structures. So there are structures of different sizes, and there is an energy flow. It goes from large scale to smaller scale, and finally goes into particles at small scales. Of course, there are particles here too, but this is the thing. I mean, this is not energy flux like Poynting flux in electromagnetism. There's no energy going across the surface. It is energy going from one scale to the next scale. Okay, the analogy I can make is money supply from central government to state government to district level and so on. So that is the supply we are talking about. It's multi-scale transfer, and this is a scalar. Okay, this is not a vector. The supply, energy supply, is a scalar. It's basically quantity going across. And here, this part is non-equilibrium. This part is non-equilibrium, and this part is equilibrium, quasi-equilibrium, I would say, because energy is going into it. So there is heating of the flow of the particles at small scales in the same bucket of water. It's not that it's elsewhere. So that is why it could be the origin of non-Maxwellian kind of distribution in some systems. Like in thermal convection, we see more non-Maxwellian all the time because it's getting heated up at small scale. So, so it is quasi-equilibrium and not equilibrium. And it's very apparent from here. I mean, we have the same system where there are some scales, it's non-equilibrium, and some scales are equilibrium. But I think many people don't notice it. This is very simple in turbulence. Okay, so thermodynamics you can apply here at small scale, but not here. Thermodynamics is not applicable here. In fact, we cannot define entropy for Euler flow where viscosity is 0. We can define, but it's 0. In fact, entropy is constant. It's Landau-Lifshitz stuff. So I think one has to be careful when you apply thermodynamics to fluid turbulence straightforwardly. I mean, you need to modify things. Now, this is a flux. In hydrodynamic turbulence, it gets changed in other flows. So flux is constant. Then flux decreases at in the viscous regime when viscosity starts playing a role. And in this regime, which is thermodynamic regime, where there are particles playing a big role, here fluid description will not be valid. We need to work with kinetic theory. And this part, I would say flux is very tiny, if at all. Flux is probably 0. This part, I would say that we should put more focus. There is some simulations at present in this regime by Srini's group in US. But I think more work needs to be done to explore this part. Now, let's just look at quantitatively. These are just words. Some people don't like it. So we can make it quantitative. This is all known very well from 1950s. Of course, if you look at real space description, then 941, which JKB described in the morning. So here, this is the equation. We convert it to Fourier space. So I just do Fourier transform. The nonlinear term is coming from here. And that becomes a convolution in Fourier space. This is a convolution. Now, so this is the equation for velocity field. We can describe, we can construct the equation for the kinetic energy, which is mod UK squared. And equation for that is this. It's a standard, but just for completeness, I'm showing you here. So the energy transfer term, that energy, wave number k, is getting energy from other modes, right? The P and Q modes. This is like field theory. I mean, this is like 5-4 theory. We'll come to it when we do coarsening. This energy coming into K mode via nonlinear transfer. Okay, and this is what leads to flux. Okay, so this we call it TUK. This is standard thing in hydrodynamic turbulence. We can call the same in condensed matter physics. This is what something I've been thinking about. This formula is not specific to flux, is not specific to hydrodynamic turbulence. Flux can be defined for all non-equilibrium systems, I would say. Okay, I mean, we tried quantum turbulence. We can also define for coarsening, 5-4 theory, all of it you can define. So take the nonlinear term, take the TUK, and is the energy. So energy is the quadratic term, okay, mod UK squared. It's not same energy as you may call 5 squared minus 5-4, that kind of thing I'm not talking about. Is a Fourier mod UK squared by 2. Instead of U, we can have scalar field phi or whatever we like. So we have to define this, we call it modal energy. Okay, and it's a energy transfer from all the modes inside the sphere of radius k0, okay, to modes outside. And this is a formula. So we can define it for 5-4 theory. It does not require a exact relation or some kind of conserved quantity. Okay, even if there's no conserved quantity, we can define flux. I think that's misnomer. I think hyped unnecessarily that we need a conservation law. This flux, in fact, is defined very often that nonlinear term we can define flux. It's the energy transfer. Okay, now what is the generic picture? You may say, well, this is for fluid only. We may have equation like for TDGL or Landau-Ginzburg. We'll have some equation which is there is a nonlinear term which is function of phi plus viscous term. Okay, or any term. Okay, so now we can go to Fourier space and we can write down. So this becomes Fourier transform of this term, which will be convolution multiply phi star k. That is my TK. And now I can just define integral, which I did all the more. So flux will be K0 is that integral TK from 0 to K0 with a minus sign in there. Okay, so this flux. Now we can define not only for systems where we can get this, but also let's say we cannot think of earthquakes. You know, earthquakes, we supply energy at large tectonic plates, and that those energy gets supplied to small scales, and finally at dissipation at a very tiny scales. Well, very tiny, of course, it means meters and tens of meters, but there's energy cascade in some kind of tearing of a paper. We supply energy at large scale that go down to the small scales. In astrophysics, there is a supernova, and that supplies energy at large scale, and that finally gets dissipated at small scales. So there is a picture where there is energy supplied large scales and it goes down to small scale. So let me just, for humor, I would say I eat food at large scale, you know, I eat at my mouth, and that gets finally to the cells. So there's energy transfer in my body. Okay, I'm going to come to that bit later. So there's a energy transfer even in quantum mechanics. Okay, like superfluid turbulence, there's energy supply, which the talk by Sankalp Ghosh. So there's energy supplied large scale, and there's a dissipation in small scales. So that is a generic picture. And so this flux is not specific to fluid turbulence. We can apply to elsewhere. And that is why I would thank Sanjay for this enlightening me to get into this field. And this work is with Ram Gopal, who has been very enthusiastic colleague. And we have been trying to do this. So he will probably present, I mean, we'll probably write it up soon. So the idea is the following for coarsening. So as I said, in 2D turbulence, we have this random flow of vortices, and finally it gets into this structure, but there's inverse cascade. So we wanted to look at whether the inverse cascade or not. So let's start with TDGL equation. Now this equation has, you can see that it has a steady state solution. So one solution is zeta equal to 0, of course, is trivial solution. Zeta equal to 1 is also a solution, plus minus 1 is also a solution. And of course, there's one solution which is often studied is zeta. So we can cancel zeta. So 1 minus zeta squared is minus this equation. And this equation leads to that 10 hyperbolic solution, which is there in Sanjay's book. But this solution is also a solution, like Sanjay himself pointed out in his summary talk, that we can get a flat solution. Okay. Now, how do I get this from energy transfer perspective? Okay. Of course, we just derive it. It's just straightforward here. But can we derive it from energy perspective, energy transfer perspective, and see whether it is forward cascade, backward cascade or not? Okay. Now, this was also, there was postdoc, Sajdev was there, and we started this work. So we look at energy equation. Okay. So mod zeta squared. And so the nonlinear term, which was zeta cube, leads to quartic term, is 5-4 theory. This 5-4 theory is known to everybody in condensed matter physics. And these are linear term zeta, k, which becomes quadratic. And this is the viscous term, which is Laplacian zeta term, which will give you k squared zeta k. Now look at the picture of hydrodynamic turbulence, K41 theory. This term is a positive sign, right? So that is going to increase zeta. This is an energy source. If you look at the picture of Kolmogorov theory, this supplies energy to the system. This is killing energy in the system, minus, it's like viscous term, okay? But of course, this is applicable at all scales, k greater than 0. Okay? So this is viscous term, this is energy supply rate. And this term is the flux. This will give the flux if I do the integral. Now it to me is obvious. Okay, it took me some time to think about it, but once we write this equation, it's obvious. We supply energy, give a random initial condition. Okay, we give a random initial condition in real space, but in Fourier space, it could be flat noise or whatever. This guy is going to start killing. Okay, so I forgot to make this picture, which I told in for hydrodynamic turbulence. We supply energy at large scale, energy dissipation at small scale. So the scale separation is important, and there is a cascade. So we need the scale separation, and we need dissipation at small scale. Okay. Now here, this dissipation is not only at small scale but everywhere. It's just getting it out. But so whatever energy is there, this is also trying to supply. This is not a conservative system in that way. It's not a closed system. So this supplying energy, but this is killing everywhere. So this keeps killing, and this term gives a forward cascade of energy. This leads to forward cascade of energy. So whatever is there at small scale, you just keep supplying. So there's basically a demon sitting here who is killing the energy, and whatever energy at large scale or any intermediate scale, it just cascades. So in fact, we found that the cascade is positive. There's no inverse cascade, and it just gets killed. But what leads to the structure is we should get zeta equal to 0 as a solution, right? In hydrodynamic turbulence, zeta, we leave it there, the kinetic energy goes to 0. It turns out, no, here k equal to 0 mode cannot be killed, right? Because for k equal to 0, dissipation is 0. So k equal to 0 mode survives, and we can match these two terms to get k equal to 0 solution. Okay, so k equal to 0 mode survives, and that's a flat solution, either +1 or -1. We can carry this analogy to Cahn-Hilliard as well. Cahn-Hilliard too has a positive cascade, but there we have k squared here and k4 here. So the spectrum is a bit complicated, but it's similar picture qualitatively holds. Okay, this part is about, so there's a flux, and we can basically make an analogous picture to Kolmogorov theory. It's not exactly the same. We see, here there's no viscosity sitting here, but we can get this flux picture to give us some good insights. In thermal convection also, we got very good, interesting insights to say that it is Kolmogorov theory, not Bolzhino-Bokov theory, which JKB described in the afternoon. Now, let's look at arrow of time. This is something which I have been thinking about for a while. So energy flux can give you arrow of time. Okay, so that is what I've been thinking about. Of course, I'm not against second law. The second law is great. It works. But for non-equilibrium systems, this gives another perspective. Okay, so just to give a picture to some students who may not be aware of it, what's the fundamental problem? So many force or Hamiltonian are time reversal symmetric. So T going to -T, equations are the same. So for example, Newton's law under gravity is the same. Also, so it turns out the forward motion and backward motion are equally probable. Okay, or in some other way, we want to be technical. I have some time. I have 10 minutes, I believe, roughly. So we start from, let's say, think of a ballistic missile. Well, then let's not think of particle. Okay, I want to come to that bit later. So think of a particle which is going from left to right, a ballistic particle under gravity. So it's a parabola. No friction. No friction. So no friction. So this goes a parabola. So this particle now it's going down. Now, if I revert it back, let's record a movie. So we make a movie. So this is a movie parabola going from left to right. Now, if I play the movie backward, then I'll see that this particle is going backward. Okay, so this is the motion of the particle going backward. Now, somebody plays the movie, then say, well, tell me either it's a real picture of some particle going from B to A, or is it a movie? Can you contrast it? It turns out we cannot, because if you take a particle at B and shoot it leftward, then we'll get exactly same trajectory. Okay, so we cannot differentiate the movie played backward with some real trajectory. Okay, so it turns out the microscopic laws are for time reversal symmetric. These are only possible for time reversal symmetric Hamiltonian, which is not the case for weak nuclear, but electromagnetic and gravity, this is the case. For particle interactions, we play the movie backward, we cannot find out whether it's played backward or is some real system. Now, let's think of turbulence. In turbulence, we have, as I said, we stir the fluid, or don't stir it. In fact, let it be decaying turbulence. We give some initial velocity and it decays. Okay, it's decaying. Now, I want to know whether it's time reversal symmetric or not. Well, it is definitely not, because of the friction force. I'm going to come to that in a minute. So it is going forward. But now to reverse it, I need to reverse the velocity field, right? That's what I said. You reverse the velocity field and let it go. Now, what happens to K41 law? This is Kolmogov's theory, which is equivalent to phi-third law. So if I reverse the velocity field, then the sign of the left hand, well, this becomes negative. So the sign will change in the right hand side, and this epsilon u will become positive. Instead of minus epsilon u, it becomes plus epsilon u. So it will give rise to energy going from small scale to large scale. So there will be some kind of inverse cascade, and you will find that these structures will start growing, but that doesn't happen. In 3D turbulence, structures do not grow. Structures basically, the energy flows from large scale to small scale. So I can contrast the forward movie with the backward movie. So these energy transfers, which is positive for 3D turbulence, gives you a clue that there is a breaking up time reversal symmetry. Now, this looks like a very good picture, and it's not specific to hydrodynamic turbulence. You can find it in all sorts of things, like earthquakes, even eating food in my biological clock. So there is a certain direction of energy transfer. So only problem is this viscous dissipation. Now, I said, well, I mean, some people say, well, friction is a dirty force. Okay, now we don't want friction. That's not fundamental. But look, I mean, I believe friction is not a dirty force. In fact, it's there everywhere. Okay, how is it there? So let me just make a slightly cartoon. So typically, Boltzmann gas, we have these particles which are given random velocities. Well, that's what I've seen. Okay, I'm not an expert of StatMech, but typically they have random velocities, they scatter, and we can't differentiate between particles going backward or forward. Let's play slightly different game. That's what I've been asking people who do simulations. There are some simulations, but not exactly what I'm after. So we have these particles, all these particles, but we let it be have random velocities, but we want certain vortex flow along with the random velocity. So we want to give some kind of vortex velocity here, like that. Okay, so we give a mean velocity, well, mean rotating velocity to the flow, and let it go. Then what is going to happen? So here is very well known in at least hydrodynamic community or plasma physics community. The coherent velocity is the mean velocity, at coarse grain velocity, not mean velocity. Coarse grain, we average a different scale. So we get velocity is function of r. Okay. Now this velocity is coherent at large scales or intermediate scale, and it dissipates at small scales. In this simulation, I'm quite sure there will be cascade. Okay, quite sure. Of course, we need to see it. There are some simulations which show it, but exactly from Boltzmann gas, we should see that. So essentially, what is dissipation? This is a, I would want collision to be elastic. Here, there is no kinetic energy loss. If you look at the total kinetic energy, but there is energy transfer. So what is going to happen? The coherent energy at large scale and intermediate scale, which is the fluid energy, which is what we call fluid energy UR, is going into incoherent energy at small scales. Okay, this is Landau-Lifshitz stuff. I'm nothing new, but we just had to give this velocity at large scales and see whether this cascade, and there will be cascade. This is what we do in hydrodynamics. We do kinetic theory and momentum integration, and we get that. Okay, so this is what. So what is the dissipation? Dissipation is energy transfer from coherent states to incoherent state, which is there, like friction of a block moving on a table. So total energy of the block plus molecules on the table is constant. However, the block energy, which is coherent energy, is going into friction energy at small scales. Okay, it's a transfer.
Professor,
yeah,
Barma,
yeah,
could you please wrap within 2 minutes?
Yeah, I will. Okay.
Okay. Okay.
So this is simulation which has been done by this group. So this is discrete simulation Monte Carlo. It's like molecular MD, and they get 5/3. So there's a cascade. It's not exactly Boltzmann gas, but they apply large scale vortex in there. Now, I just want to, re-emphasize that total energy is constant, but energy transfer from one scale to next scale, and that is what is friction. So in quantum fluid 2, there is superfluid. We can apply large scale forcing. These experiments have been done, and we get 5/3 law. Well, not exactly like Kolmogorov turbulence, but 5/3 is there, pretty similar to Kolmogorov, not exactly. And supposed to be the phonons at small scale are supposed to take the energy out. Superfluid has zero viscosity, but there is certain microscopic energy sucking out, and that is what there's a friction in it. And as I said, biologic also has friction. So I just want to make the last cartoon. Now, I hear this talk. So I say, well, why we age? Why don't we grow younger? Now, looks like it's a very ridiculous question, really, if you think about it. Now, what does it mean by reversing the velocity from this toddler to I become like this, okay? Now, what do I mean? I need to reverse the velocity. It's not going to happen automatically. Nobody's going to reverse the velocity in my body. If I just imagine that we reverse the velocity, I will be breathing in carbon dioxide and breathing out oxygen. Like that's, so I think reversing velocity is not possible. This is a very, this is not an experiment which we can do. I think reversibility is only true for idealized systems, especially particles. Okay, we can idealize reverse the velocity, or more importantly, we can say that forward motion and backward motions are equally likely. That's what I can think. I thought about it. That's what we think. Just imagine. Well, we can have many more ways to break time reversal symmetries. I'll just give you one more example or several. So here, just imagine Boffer's ball coming out with this shell coming out and reaching here. Particles we can reverse, but what about, can we reverse this? Take the Boffer shell, if it doesn't break, okay, it will of course explode. If it doesn't explode, push it back. Will it go in the muzzle? No, it is not going to go in the muzzle. It requires, even if you try it, there will be enough random velocities and so on. There's friction all the time. So multi-scale systems, we cannot do it, okay? There's a microscopic systems do not have this time reversal stuff. So nonlinearity will break it, which is there in standard thing like initial condition matters. I agree with that. But there are other things like structures, forcing. Force oscillators does not have time reversal symmetry, okay? Structures, they say, well, there's a satellite moving, we can't reverse it. So time reversal symmetry is broken in microscopic system, and we don't need to invoke reversibility of microscopic fundamental laws. It is there because of its too complicated system. Anyway, so I will close here. Multi-scale energy transfer is useful diagnostics for non-equilibrium systems. That's what I would. Okay, it's obvious, but and again I thank the organizers and wish Sanjay a very happy birthday and very healthy life in future. So I'll stop here and I welcome any questions.
Okay, thank you, Professor Barma. Now there is a question answer session. Ramu Gopal want to ask question.
Okay.
Ramgopal, yeah, please. Yes. He raised the hand. Please raise your hand again. Okay, yeah, yes. Please, yes, okay, yes.
I can't see the chat
Hello.
box. Should I see the chat box?
Now he can unmute himself, sir.
So,
Meanwhile, I have a question.
Yes.
please, yeah, go ahead.
Yeah, very nice talk, particularly this time reversal issue. In physics, when we teach students, we ask them to, find out the probability that we can reverse the velocity and so on. And it becomes more and more improbable because of Poincare recursion cycle when you deal with more degree of freedom. But the point you have brought out is very important, because when you look at coarse grained degree of freedom, in a very natural way, the time reversal is coming. That's what you are trying to say. So I will think about it. It's very nice. Yeah. Thank you.
Thank Professor Bhaskaran. Thanks for kind words. I hope.
Can you hear me now, sir?
Yes,
Yeah.
Ram Gopal. Yes.
Yes, sir. My question is related to vortex formation in two-dimensional turbulence. The vortex and anti-vortex are also formed in two-dimensional XY model, and
Yes.
their winding give rise to a transition from paramagnetic phase to a quasi-long range order phase. So my question is, what role the vortex and anti-vortex play in a laminar to turbulence transition?
Okay, it's a good question, Ram Gopal. I've been trying to think about this, but one thing is the XY transition is an equilibrium transition. So at some temperature we get this separation, like in water to vapor transition. So it is not exactly like 2D turbulence, but yes, the interactions become strong enough, then entropy loses and we get success. 2D turbulence, so that's number one. It's so there's a remark, thanks for reminding it. Equilibrium phase transitions are different. Equilibrium phase transitions are zero flux, because we fix a constant temperature. We need a TDGL. TDGL is non-equilibrium. There is basically things are evolving. That's what my understanding is. I may be corrected. Second, in fluid turbulence, also we have cyclone and anticyclones, one way and second way. In 2D turbulence, they are approximately same number. Not okay. We'll get same number. That is conserved. When you bring in rotation, then one becomes more than the other. Okay. Finally, we'll not get one vortex, but always get pair of vortices in 2D turbulence. Okay. So I think that's what you get in XY transition. If you bring in dynamics, then we'll get some cascade, but yes, I guess you get also pairs, right? In XY model.
Yes, yes, they are pairs, vertices and anti-vertices.
Yeah, so
and
that
anti-vertices are opposite winding.
Yeah, I think there are a lot of similarities. Yes, but the flux is the only difference, I would say.
Okay.